So we've practiced revolving a region around the x-axis and around the y-axis. We only have 2 more new kinds of cases to consider before we're done with Chapter 7, with first semester calculus. Congratulations, you are so close. So, 2 possibilities. One possibility, what if we have to rotate around a line that is neither the x-axis nor the y-axis? So you'll recognize this picture from your free response notebook, but don't rush to your free response notebook and do this work, because I've changed the problem so I can show you an example of what to do when you have to rotate a shape around an axis that is in fact adjacent to the region. So R is already marked. I've been asked to rotate R around sort of R's top boundary. In this case, it's the horizontal line y equals 6. So I'm going to take that shape, and I drew in the axis of symmetry. R is already shaded. Let's see, my reflection would be something like this. Oh, I was trying to draw an upside down R. I didn't get it. Okay, well that's upside down R. So now what's going to happen? If I try to draw in a slice, I'm going to get my green marker here. I said I'm going to start at the axis of rotation. I'm going to draw toward the far edge of the shading, come back up behind the axis of symmetry, all the way to the far end of the reflection, and back to the rotation of the axis of revolution. So that's a slice. So the question is, what is the radius of the slice? That's the only thing really left to figure out in any one of these revolve a region around a line kinds of problems. So I'm going to try to draw in the radius of that green slice. I'm going to start in the center of the green circle, in the center of the green slice, I'm going to start my marker at the axis of revolution. I'm going to draw toward the far end of that green circle. It really should have made it all the way down to here, right? Okay, here's the question. How long is that blue vertical line segment? So imagine a picture. Okay, so I tried to make a similar little picture here. The top boundary of my blue radius is the line y equals 6. The bottom boundary of my blue radius is this function y equals, let's make it blue, 4 natural log of 3 minus x. And down here at the bottom, I have sort of this bottom boundary, which is y equals 0. So just notice that if I said that the blue radius had distance 4 natural log of 3 minus x, that's not true, because it's this distance, which I will make orange. This distance is 4 natural log of 3 minus x. If I want to figure out the distance along the blue radius, it's going to be top minus bottom. And in this case, the top of the blue radius is always 6 minus the bottom of the blue radius. That's the 4 natural log of 3 minus x. So just notice when your radius, your axis of revolution, is not one of the coordinate axes, so not x equals 0 or y equals 0, then you're going to have that number from the line of revolution in an expression for your radius. So the bottom part here would have been 4 natural log of 3 minus x. But the part I want, that blue radius, it's 6 minus 4 natural log of 3 minus x. So now I can write my integral. I already said that I was taking slices that are perpendicular to a horizontal line. That means my slices are vertical, which means I'm integrating with respect to x, and the thickness of every slice is a dx. I actually write my integrals in this order. I recommend you do too, because even if there's parts of it that you can't fill in or that you fill in wrong, you can get partial credit. So if I'm integrating with respect to x, my limits should be x limits. this picture, well, this region R goes from x equals 0 to x equals 2, 0 to 2. Sometimes I write in an intermediate answer, which is going to be, I'm going to integrate pi r squared. Now, to clarify, that little r has nothing to do with that r. It just tells me that every slice of mine is going to be a disk, and the volume of a disk is pi r squared times thickness. So if I wrote this and left it on the AP test, I would probably get 1 point for getting the limits and this constant pi in the right spot. And then I would come back and I'd fill in the rest of this. This is going to be pi times the integral from 0 to 2. My radius, we said, needs to get squared, and the radius was 6 minus 4, natural log of 3 minus x. This is a calculator problem, so I'm going to type that into my calculator. So I typed this in to show you that I typed the pi first and then the integral, although you could put the pi inside. When you want to integrate, here I'm integrating from 0 to 2, and you know that you're going to take a radius and square it, your very first type inside the integral should be an extra pair of parentheses. So even though the integral opens with an open parenthesis, you should put in another open parenthesis so that you can have, here I've typed in my r, so that closes the 3 minus x parentheses, that closes the natural log parentheses, that closes the extra parenthesis I typed in, and I have the square on it. That's the parenthesis that was typed in already. That closes the integrand, and then I typed in the dx. So 24.766 equals 24.76.